Hi, everyone, and welcome to my talk, Life of a Vulnerability. My name is Dana, and I work for the Chrome security team. I am here more or less reusing slides that Adrian created and presented in the past, so many thanks to him for his hard work. Anything in this talk applies to all web browsers, so if at times it comes off as a bit Chrome specific, that's not the intention. Don't forget to ask questions on slido.com. The hashtag is Chromium, and we're in room B. I'll be happy to answer any questions that there are. So today we're going to talk about typical vulnerabilities in Chrome. We're going to talk about who attacks them, how they attack them, and how you can prevent that from happening. I'm going to start with an unsolicited quote from one of our VRP bug reporters. Here, the Chrome team or the web browser developers at large, we're the goodies, and we're going to meet who the baddies are later. We're going to look today at one specific vulnerability for the context of this talk, which really was exploited in the wild. CVE here stands for Common Vulnerabilities and Exploits. This is a global database of software exploits so that each one can be referred to by a unique ID. So in this case, CVE 2019-5786. Here's the timeline of this bug. The steps leading up to introducing the bug, the attack that happened, and how we discovered and fixed it. You'll notice that the vulnerability was present here for quite a while, from 2015 till 2019, and we didn't know how long it's been exploited when we discovered it. But first, you might wonder, how on earth are we so bad? How do we manage to have exploitable bugs in the first place? I've stolen this slide from another Chrome University course, but it serves to show we have the most complex security boundary in the industry. We take internet content, which is an entire ecosystem, an entire platform, an entire industry, and then we process that. We have to keep it locked down safely and convert all of that complex content, being HTML, CSS, JavaScript, quick, speedy, TLS certificates, WebRTC video content, WebGL, you get the idea. We have to convert all of that into pixels and interactivity in a safe way. That would be hard, but we make it even harder. We have to do that on the user's own devices. They come with diverse operating systems, and they are full of the user's most precious secrets. It's harder because they're heterogeneous, but it also means it's extra critical that we get it right. This makes it, I would claim, the hardest security challenge in the world. We have to pull an entire industry of content onto someone's private device and keep their device safe. So how are we attacked? It's really all about the data. An attacker will craft malicious data, which is designed to trick our code. So the most important thing to think about, where your data comes from. Think about what data is untrustworthy. Unless you can cryptographically prove that that data comes from us at Google, you have to assume that all data from the internet is untrustworthy and may contain attacks to exploit your bugs. TLS does simplify things. If TLS is working properly, then you can be sure that the data you're processing really does come from the web server, as opposed to some man-in-the-middle attack on the network. And TLS adoption has been increasing dramatically, which is great. But even though you can trust it came from the web server, a page is often composed of content from many web servers. A typical website today embeds many other websites through images and iframes, especially for ads, which come from a third party the main page does not control. So it's important to assume that all data coming from the network is untrustworthy and work your way back to what you can actually trust about the data. So let's move away from the data for a second. Let's look at the code which processes that data and how it gets bugs in it. We have a lot of bugs. This chart just shows high and critical severity security bugs. Most of them, fortunately, are found by our internal fuzzing infrastructure called cluster fuzz. If you were just in the fuzzing 101 talk, you may have heard about this. Mostly, they're found by cluster fuzz before the code gets to our stable branch, which means before they get to our users. But quite a lot are also found by our external vulnerability rewards program researchers. These are kind souls who report security bugs to us in return for money. Many of them donate that money to charity even. They're really awesome, and they are also always keen to help. So don't be shy to ask them to test fixes for you, to help you reproduce in different ways, etc. So let's talk a little bit more about Cluster Fuzz. Our high-level goal is to find bugs before they get shipped, and failing that, before they are discovered externally. Cluster Fuzz is one of our best tools for achieving that. It's continuously generating random bits of data to feed into Chrome to see what goes wrong. In fact, it's not random. That's not quite right. It generates some input and then gradually evolves that input to increase the code coverage and explore more of your code until it crashes. If you add new code which handles untrustworthy input, you should add a fuzzer for it. This can be just 2 lines of code taking the input data which Cluster Fuzz generates and passing it to your new function. It's really that simple. Then you'll get the benefit of 25,000 cores exploring your code to look for any mistakes. How awesome is that? If you're adding or changing a Mojo API in particular, we have a toolchain called Mojo LPM to make writing fuzzers against Mojo APIs super easy. Interested external researchers should take note. They may want to look into this as well as a nice way to find reportable bugs. On that note, it's worth pointing out that adversaries also write fuzzers. So Cluster Fuzz is really in a race against bad actors to find all of our possible exploits. By contributing fuzzers for any new untrustworthy data, you help ensure that we find the bugs first and can fix them before they get used maliciously. For more on this topic specifically, please check out the Fuzzing 101 talk that just happened earlier. The video should be available shortly if you missed it, and Googlers can follow the Go link. In addition, there's a Go link for Mojo LPM, which is just a shortcut. It's a document in our source tree. So let's go back to the timeline for this specific bug. You'll notice immediately that there are 4 separate events which led to the bug being introduced. At no point was anybody stupid, and in fact, some of these changes were specifically done to improve security. Each one was done with good intentions and looked fine on its own, but it was the emergent behavior from those changes interactions which resulted in the bug. Let's look at some of those steps which led up to the bug being introduced. The attack was in the form of malicious JavaScript delivered to Chrome. It used 2 major APIs. One of them was PostMessage, added way back in 2009. It is used to send messages from one browser window to another. Originally, PostMessage only allowed you to transfer strings. In 2012, that restriction was relaxed, such that certain objects could be transferred too. Objects are transferred via the last parameter, named transfer. You can use that to give JavaScript objects to the other window. Note that it says the ownership of these objects is given to the destination side, and they are no longer usable on the sending side. Remember that. It'll be important for understanding the exploit. That means from the point of view of the sender that the JavaScript object is deallocated. From our timeline, we can see where PostMessage was first introduced, and the ability to transfer objects with it came a few years later. In between these 2 events, the file reader API was created. Here's the file reader class. It reads files, but specifically, it can read them into another type of JavaScript object called an arraybuffer. So through this method, file reader.read as arraybuffer. Our exploit will be using this. The final step, which introduced this bug, was an optimization to the way our JavaScript to C++ bindings worked, partly to make them smaller, and in fact, partly to squash lots of other security bugs. So let's talk a little bit about those bindings. JavaScript is supposed to be a simplified world without access to the innards of the browser. JavaScript should not be able to escape its own controlled universe, which means it should never see a C++ pointer. But most objects and concepts in JavaScript are in fact backed by C++ implementations within the browser. And in this case, one of those objects had a bug, which enabled JavaScript to manipulate C++ memory and pointers directly. A JavaScript API, as I mentioned, is backed by a C++ implementation. And here's the C++ implementation for FileReader.read as arraybuffer. The first snippet of code doesn't matter too much, but we note that it is in the read as arraybuffer method that we saw a minute ago, and within this method, it calls the second snippet arraybuffer result. The second snippet has the bug. Can you spot it? Remember, this is a bug which enabled an attacker to gain full control of a machine. You probably don't see it, and that's exactly the point. It's very, very easy to introduce memory safety bugs. This type of bug is typical. You won't spot that you're doing it. And if there's one thing to take away from today's session, remember that. You will introduce memory safety bugs. All this snippet appears to be doing is creating a DOM array buffer to point to the file reader's data. So let's look at how that went wrong. Here's the layout in memory, in some imaginary computer with 20 bytes of memory. The DOM array buffer object is a C++ peer object that corresponds to the JavaScript array buffer object. Importantly, it doesn't store the actual data buffer. Instead, like a C++ vector, it has a size and a pointer, which refers to another bit of memory allocated by C++, which is called the backing store. So what happens if somebody calls FileReader.read as arraybuffer again? A new DOM array buffer is created, corresponding to the JavaScript object which was returned. But for efficiency, that doesn't always allocate a new copy of the backing store. The file might be 4 gigabytes big after all, so we don't want to make another copy. Instead, the new DOM array buffer can refer to the existing copy of the backing store. Now, let's use postMessage on one of our JavaScript array buffer objects. Remember, if you give an object a postMessage as a transfer parameter, it is no longer usable on the sending side. Specifically, the C++ backing object is deallocated. So there it goes. It's deallocated in our window now, and the JavaScript object disappears. With it, the corresponding C++ object is deallocated. However, here's the bug. The C++ object believes that it owns the backing store, so it also deallocates the backing store. Sadly, we have another JavaScript object, which was pointing to the same backing store. So now we have a JavaScript object pointing to an area of RAM which C++ believes is not allocated to anything. This allows JavaScript to read and write to this unallocated space. This type of bug is called a use after free. You probably didn't spot it in the C++ code where it was introduced, and that's okay. It's very easy to make all kinds of memory safety errors in C++, and you should assume that you will do so. That's why it's really important to take basic security steps with any new code, running it in a sandbox, fuzzing it, etc. We'll talk more about it later. So now that we've introduced the vulnerability, time passes, and we don't know how much time. But eventually, somebody found that vulnerability. We don't know if they found it through fuzzing, through code inspection, or some other means. So who are these mysterious people that find and exploit vulnerabilities? You might have this stereotype in your head that it's the teenagers in bedrooms, and sometimes that's true, but not always. Sometimes they're countries. But above all, we need to defend against an industry. Vulnerabilities and exploits are bought and sold on the open market. There are businesses which research software to find vulnerabilities and then sell those to the highest bidder. Some of them explicitly limit who they will sell to based on ethical guidelines. For example, not selling to terrorists. However, others choose fewer limitations. So there are many such vulnerability brokers all over the world, and there are many researchers working to find exploits and then sell them to a vulnerability broker who sells them to an attacker, typically a government. How much these vulnerabilities sell for, you might ask? These prices on the left-hand column here go up to $1 million. That may seem high, but think about it. If you're a bank protecting more than $500,000 of money, it's economically rational for someone to buy a Chrome exploit to attack you. That's not a lot. It's also not a lot if you're attacking a dissident in an oppressed country. Some suspicious types may be willing to pay even more. A kind external researcher shared with us that they were offered $500,000 for just a Chrome remote code execution alone, without the privilege escalation out of the renderer sandbox. The prices tend to go up as we close other known bugs. You might also wonder why a Chrome vulnerability here is worth 5 times more than an Edge, Safari, or Firefox, and that's just a function of supply and demand. Because Chrome is the most popular browser, an exploit for it is much more likely to be useful than for attacking any particular target. So more can be charged for them. It would be nice to think that the market pressure of more valuable exploits also helps us to increase our security, either through our reward program or through our engineering investments. But just to be clear, this is not at all theoretical. Our bugs are exploited by this industry. Some organizations and researchers are kind enough to blog about it. These nice people here have 3 different posts about different Chrome bugs. They wrote about watching for interesting commits that could be fixing security vulnerabilities, and then writing exploits against them. Those exploits would work on the current and previous stable versions of Chromium. This is another blog post about a bug from summer 2019. And from reading the blog post, it looks like they had a vulnerability which we accidentally fixed with a refactoring. Lucky. And here's another from just a few weeks ago. This was posted to securitylab.github.com. So let's go back to the timeline. Some attacker discovered this bug. They traded it across the industry, and somebody somewhere is going to use it. In this case, who? In this case, it was a threat group in South Korea. They were attacking North Korean targets with it. Thankfully, our threat analysis group allowed us to share this for the purpose of this talk. We normally keep this type of information very secretive for obvious reasons. Let's look at the attack code. As ever, it was some untrustworthy data. In this case, it was some JavaScript delivered by email or at watering hole websites. It's pretty simple, so let's just walk through it. First, the attacker allocated a file reader. They asked it to load a file. That's at the bottom, the read as arraybuffer. But they also registered a progress update handler. Obviously, files can be huge and take a long time to load, so the file reader API can call an occasional callback with progress information. Within that, the attacker did the cunning thing. They asked for the arraybuffer twice. That's buff1 and buff2. Sometimes this would give 2 different array buffers pointing at the same backing store. If the attacking code found that, they'd deallocate one of them by using post message. And hey, presto, they have a JavaScript object pointing to some C++ memory that is considered unallocated. This was the real attack code, though there's 2 small changes. First, they used 2 read as arraybuffer calls, but I ran out of space on the slide. And second, I replaced the number that they wrote to memory with the number 42. While 42 is not obviously useful here, you can imagine other numbers could be, such as memory addresses. So when the attack succeeded, they have a pointer that lets them read and write memory, whatever they want within that old backing store's space, simply by reading and writing from their DOM array buffer or their JavaScript array buffer. This is a super typical type of bug. In fact, 50% of our bugs were used after freeze in this year. Memory safety of other types, for example, a buffer overflow or a type confusion, take this up to nearly 80% of our bugs this year. But how is this a big deal, you might wonder? The attacker can now write to a small bit of memory, which we know C++ considers to not be allocated, but that's almost by definition pointless, right? This memory is not being used. So I'm here to tell you that attackers have this huge tool chest of clever techniques that they can take any such small chink in our armor, and they can use it to enable more powerful attacks. It's not my goal to list or explain what sort of techniques all exist. There are many, and I surely won't know them all either. But the point is to show you that even this sort of small, seemingly insignificant bug really can be exploited. And in this case, really was exploited, thanks to this armory of techniques. I also want to point out that we try to make each step in this chain more difficult with various mitigations. And I should also note that the following explanation is not precisely what happened in the exploit we're studying for the purpose of this presentation, but it's a realistic path that such an exploit can take, and there are many others like it. Here's one example of such a tool that can turn a small exploit into something more powerful, which is called a heap spray. It will allow the attacker to use this read-write in the deallocated backing store and turn it into a more powerful read-write in another JavaScript object. To do this, they simply allocate lots of objects from JavaScript. That's it. Eventually, one of them will happen to be in that block of memory that they can write to. And as you can see, the name Heap Spray is pretty well descriptive of this tool. So what happens, now they have this other JavaScript object allocated in the area that JavaScript can write to. The attacker has been cunning. They chose that JavaScript object to be itself an object that has inside of it a C++ pointer. The result is that the first exploited JavaScript object in green allows them to now read and write a C++ pointer from within the second JavaScript object in pink. Then that second pink JavaScript object can use that pointer that is now fully under the attacker's control. Once they can overwrite a pointer, they can read and write memory absolutely anywhere in the process. So that's one way to turn a use after free read-write into arbitrary memory access from within JavaScript. I'm not going to talk through any other attack techniques, but if you've heard of terms like return-oriented programming or NOP sleds, these are both other examples. There's many of these techniques, which can be used to take any vulnerability and turn it into something bigger. So you should rightly assume that any bug you introduce probably can be leveraged into something more dramatic, even if you're not sure how to do it yourself. Once you've got the ability to read or write memory anywhere in the renderer process, there's a lot more that you can do. Another example can be found at this link, where a single byte of buffer overflow was turned into malicious code execution through a series of such tools. The Go link is a shortcut to the larger link below. So what could an attacker do now that they've got the ability to read and write anywhere in the process? Potentially, there are other websites running in that same renderer process. So they could steal credit card details, steal your industrial designs, maybe even move your bank balance around or blackmail you. I'll talk a bit more in a while about when we would end up running several websites within the same renderer process. They could also overwrite URIs and data structures within the browser to alter its behavior. So even a single out-of-bounds read and write could have serious consequences. And you should assume that it can be used for a sophisticated attack. You should assume that it's being used for a sophisticated attack. And a renderer compromise alone is already serious. But a typical attacker wants to get further, and they want to achieve arbitrary code execution within the renderer. For example, through the use of the V8 JIT engine. It's not too hard to write native bytecode to memory and then call it from JavaScript. This is one of the most common paths for code execution in the renderer process today. But arbitrary rewrite also makes it possible to replace function pointers, vtable entries, etc., to manipulate what code will run. So we've talked a bit about how the attacker could get to run their own native code within the renderer process, essentially applying a patch to the executable. So here are some things to remember. But with most exploits, the goal of the attacker is more than that. They want to move beyond the renderer process and compromise the whole machine. So let's talk about the different processes involved in Chrome. Code execution in the renderer is not sufficient to own the machine entirely. The reason why is because Chrome has a multi-process architecture. Most of the untrustworthy data lands in the renderer process, including this particular attack. As you've seen, attackers may be able to achieve code execution in the renderer process, but that isn't enough to control everything. That's because of the sandbox. and that restricts access to the operating system facilities, such as the file system or the operating system kernel. However, some untrustworthy data does flow into some of the other processes. The network process is currently not sandboxed and obviously handles protocols such as DNS, quick, speedy, etc. The GPU process cannot be sandboxed on every platform. And the vulnerable renderer process interacts with all of these less sandboxed processes. So let's look at a couple of the process types specifically. First, a bit more about the renderer. Even bugs here can be serious. While there is a restricted access to the rest of the PC thanks to the sandbox, there might still be a way for one website to steal data from another. Imagine you're visiting bank.com, which has your credit card details, and suspiciouscatpictures.com. On most Chrome devices, they would be run in separate renderer processes. That's even the case if one website embeds the other using iframes, and that's a feature we call site isolation. But unfortunately, this is not the case everywhere. On a low-end Android device, there simply isn't enough memory to create many separate renderer processes. So they may still be living together in one renderer process. And that won't change anytime soon, as it's a fundamental limitation of the device. So if you introduce a bug in the cat parser, that might allow bad actors to steal credit card details. Maybe suspiciouscatpictures.com embeds your bank in an iframe. The browser process holds the keys to the kingdom. It has full unrestricted access to the machine, and it will never be sandboxed. If the web were an operating system, the browser process would be the kernel. So it's important to realize when you're working in the browser process, you have to be especially careful. You could never parse untrustworthy data because whatever bugs you introduce would result in unrestricted code execution. The security team recently introduced the rule of 2. If you consider the 3 circles here, code which processes data that you don't trust, code written in C++, code written outside a sandbox, such as anything in the browser process. Combining these 3 together creates a very vulnerable situation that is likely to lead to exploits. Removing any one of those circles from the equation will help to keep our users safe. I would like to note that on Android, we are able to use Java instead of C++ in order to drop the unsafe language circle. But on other platforms, we don't have that. We have aimed to introduce Rust, but at this time, that effort is still in progress. It's also important to remember that other processes can be compromised. So all IPC messages are in fact untrustworthy data and should be considered malicious, both the data in the message as well as the fact the message was sent at all. So to review, in our example, exploit chain, we saw that the attacker used the file reader, use after free, to write to a specific bit of memory. They used a heap spray to arrange for a C++ pointer to be within that part of memory, allowing them then to write to memory anywhere in the process. They went beyond that with the ability to read and write anywhere in the process. In this case, they tricked audio context into allowing them to execute arbitrary native code. I haven't talked about the details of that here. They were able to make the exploit completely reliable by repetition, so that they reliably got to this point. Again, another something to remember. Just because something is timing dependent and a bug is really hard to reproduce, don't disregard it. Assume that the attacker can load many websites, iframes, or use other timing tools to make it reliable for them. But did they achieve compromise of the whole machine? In fact, they did, but it wasn't through another Chrome bug in this case. They combined our Chrome file reader bug with a Windows kernel bug to achieve total control of the machine. But hold up, you're thinking. We put the renderer process in a sandbox to prevent it from using the operating system directly. This should prevent it from getting unrestricted access to the rest of the PC. So how did they get access to a bug in Windows? In this case, we failed, and the renderer did manage to do this. It got unsandboxed code execution, but only on 32-bit Windows 7 machines. On Windows 10, we had new mitigations in place called the Win32K lockdown, which prevented access to the relevant parts of the Windows API. Unfortunately, that's not possible on Windows 7. And on 64-bit machines, the heap spray was impractical, just due to the sheer size of the heap, and to our use of an allocator called partition alloc. They would have needed to use other tools in place of a heap spray on 64-bit Windows 7. But to be clear, it was this specific attack technique which didn't work on Windows 10 or 64-bit machines, and it's possible that their target was known to be running Windows 7 on a 32-bit machine, in which case they had everything they needed. I definitely don't want to imply that memory safety is less important on Windows 10 or 64-bit. There are other attack techniques which do work, and that could be used instead to leverage the same bug. I won't go into more detail here, but we are always working on new mitigations to further restrict the escalation of access that can be gained through any given bug. Miracle Pointer and the work going on there is a good example right now. So back to our timeline. How did we at Google respond to this particular event? At 4 a.m. on February 27th, we found evidence that this was really being exploited in the wild. By 7:53 a.m., we had a bug. One of the first things we did was feed the exploit code to cluster Fuzz. It doesn't just generate new input. You can also feed it known bad input and see if it finds a crash. By 9:05 a.m., it had found the crash. So we had a fix by 2:31 p.m. that same day. This is so awesome. And that fix was landed by 5:44 p.m. The next day, we confirmed the fix with clusterfuzz and merged to stable and beta branches. Then we started to roll out a fixed build to the world. But the process doesn't end there. It took a week for even 50% of Windows users to get the fixed build. Our users' vulnerability even increases once a fix is landed on trunk and is visible to the world, until they receive that patch in a stable update. Recall there are organizations that watch for bug fixes and write exploits against them. This is the window in which those can be used. So with security bugs, you should act quickly to fix them. But then you also need to work closely with the security TPMs to get them merged back to stable and beta branches and out to users. There's an interesting related bit here. Chromium gets used on all kinds of devices these days, from TVs to cars to who knows what. And often these devices are running old versions of Chromium. You can imagine how that might go wrong. This means that as we fix bugs in that version or in future versions of Chromium, the bugs in those devices become easier to find. Pwn to Own was held last week, hosted in Toronto, and I heard that there were multiple exploits presented against devices running old Chromium versions there. This highlights the importance of keeping software up to date. So that's the story of CVE 2019-5786. It is a mixed story. We got successfully attacked, and our users suffered as a result. Our mitigations worked on most platforms, but not on all. We fixed it quickly, but it still takes a week to get the fixes rolled out. So let's talk briefly about some of the other types of vulnerabilities we see. There's all kinds of basic C++ memory safety bugs. Recall they're 80% of our security bugs this year. Integer overflows are also a basic coding issue. Beyond that, things get a bit more sophisticated, like UI spoofing. This can be everything from domain names with similar looking Unicode characters to websites that try to impersonate bits of the Chrome UI. There are always attacks on protocols, especially encryption protocols. There are attacks on those headers which try to protect websites from one another, as well as protecting the user from malicious websites. And there's the occasional huge crisis in the CPU, which means we can't rely on any of the foundations that we've always believed in, such as Meltdown and Spectre. And there's the certificate ecosystem. So some things to remember. We will all introduce security bugs. Assume that attackers can and will exploit them and get full control of the machine or steal our users' data. So write fuzzers anytime you deal with untrustworthy inputs and that includes IPC messages. Don't parse untrustworthy data in the browser or any unsandboxed process. And don't trust other processes. Assume they are malicious. Act quickly when bugs are reported, but also act quickly to merge bug fixes back to the stable and beta release branches. And get security review early when writing new features to help ensure you have considered the security implications and to avoid or find bugs before they get to our users. We have the hardest security job in the industry for our team, but we're all in it together. So ask for help. The security team is here to help the whole Chrome team and to support you. That concludes the talk. If there are any questions, please feel free to add them on the slido.com, #Chromium. We're in room B. I am happy to answer any questions. I'll hang out here for a minute. Okay, so there's no questions coming up right now. I am super happy to answer any questions that you think of later. You can ping me on Slack, DanaKJ. You can email me, danakj@chromium.org, and I'd be happy to talk with you more. Thank you super much for coming to my talk and listening, and have a great day.